Okay, in this video we're going to look at a couple of examples of double integrals evaluated using a change of variables. So let's just recall the formula. So if we have this double integral over a region R, which is happening in the xy plane, we can transport it to a double integral over a region S in the UV plane if we multiply by this thing called the Jacobian, which is the absolute value of the determinant of this matrix built by partial derivatives, where this is giving our change of variables. So we can think about this change of variables as something geometric, taking the region S in the UV plane to the region R in the XY plane. Okay, so the first example that I want to look at is this one, which says find the area of the region bound by this curve square root of x plus square root of y equals 1, and then x equals 0, y equals 0. So in other words, in the first quadrant. Okay, so the first thing that I want to do is draw a picture of this. And first, notice that this curve only exists in the first quadrant, so that's something that's maybe important to notice. And it also goes through the point 0, 1, and 1, 0. In other words, it crosses the x and the y axis like that. And now, in order to really solve this problem, we don't need to know what the curve looks like. We can just draw anything between here and here, but I'll go ahead and point out that it looks something like that. So this is our region over here, maybe I'll call it D, that we want to find the area of. Okay, great. So now, how are we going to do that? We could probably do that without using a change of variables, but I want to use a change of variables just to show an application of this thing right here. And the change of variables that I will use will be in order to simplify this bounding curve right here, which is square root of x plus square root of y equals 1. And so what I'll do is I'll let x equal u squared and y equal v squared. And so in the language of this transformation over here, that means t of uv equals u squared v squared. Okay, great. So now let's see what that gives us. So that means that the square root of x plus the square root of y equals 1 is going to be changed into the square root of u squared plus the square root of v squared equals 1. Now that immediately looks like the absolute value of u plus the absolute value of v equals 1, but since all of this is happening when x and y are positive, that's really just u plus v equals 1. Which means we can make a corresponding picture down here in the uv plane. And we know that u plus v equals 1, well, that's the same thing as v equals minus u plus 1 if you want to think about that in slope-intercept form. So this goes something like that. So that should be a straight line. So maybe we can call this region over here d bar. Okay, good. And now notice our transformation takes this region right here, which is a triangle, and it bends the triangle a little bit. Okay, great. So now we can go ahead and calculate this area using this change of variables formula. So notice that the area of D is going to be the same thing as the double integral over D of dA. So that's going to be the same thing as the double integral over d bar. So we want to move that into the UV plane, but now dA has been replaced with the absolute value of this Jacobian. So dxy by duv, and then dA bar, where that A bar is happening in the UV plane. Okay, good. But notice that this thing is something that we need to calculate, so that's going to give us the integral over d bar of, so that will be the absolute value of the determinant of the matrix that's made up of taking the derivative of x with respect to u and v and y with respect to u and v. So that will give us 2u, 0, 0, 2v Good. And now we have dA bar, where that's happening in the UV plane. So we're running out of room, so I'll clean up the board and then we'll pick it up from there. So picking up where we left off, we have the area of the region that we called D, which was described by this up here, is equal to the double integral over D bar, where we've transported that into the UV plane, of the determinant of this 2 by 2 diagonal matrix, and then this dA bar, where that integral is happening over here. Okay, so now notice we can simplify this a little bit. This is going to be the integral over D bar of 4uv, and notice I can get rid of my absolute values because I'm happening in the first quadrant over here in the UV plane, and now I have dA bar. But now what I want to do is change this double integral into an iterated integral in the UV plane. And so maybe let's go ahead and put u as the outermost integral. So notice that the smallest u can be is 0, the largest u can be is 1. And then if we go to an arbitrary spot here on the u-axis, the smallest v can be is 0, and the largest v can be is on this line. In other words, it's 1 minus u. So that means I can change this to an iterated integral, 0 to 1 and 0 to 1 minus u. And now I have 4uv dv du. So now I'm good to go. I can finish this off pretty handily. So this is going to be the integral from 0 to 1 of, now I have 2uv squared evaluated from 0 to 1 minus u du. So I've done my antiderivative with respect to v, which is on the inside. Now that's going to give me the integral from 0 to 1 of 2 times u, and then 1 minus u squared du. Now we're almost done. I'll bring this up and then we will finish it off. So we left off here. The area of our region D is the integral from 0 to 1, 2u times the quantity 1 minus u squared du. So it's pretty easy just to multiply this polynomial off and then finish it very, very quickly. But I want to do a change of variables just to like hammer in the fact that we can make things simpler without much work. So let's go ahead and do a change of variables. We'll let t equal 1 minus u, so that makes dt equal minus du. In other words, du is minus dt, so I'll just switch that immediately. And then, good, so that's enough to, and then let's see what happens to the bounds. So notice if u equals 0, that's going to make t equal to 1, and if u equals 1, that's going to make t equal to 0. So that changes the bounds of integration. So that kind of finishes off everything we need to do this change of variables. Notice that's going to change us to the integral from 1 to 0 of 2, 1 minus t times t squared, and then minus dt. So I'm going to go ahead and change this sign by switching the order of integration. And then I'm going to simplify. So this is going to be, I'll bring that 2 out. I have the integral from 0 to 1 of t squared minus t cubed dt. But now I can just use the power rule. So that's going to be 2, and then I have 1/3 t cubed minus 1/4 t to the 4th. I'm going to evaluate that from 0 to 1. So that means I have 2, and then 1/3 minus 1/4. So let's see, 1/3 is the same thing as like 4 over 12, and 1/4 is the same thing as like 3 over 12. So this is going to give us 1 over 12 times 2 is 1 over 6. And so, good, that finishes this first example. So for our next example, we'll look at this one. So let's look at the double integral over d of xy dA. And here d is the region bound by these 4 curves. So we've got 2 lines, y equals x, y equals 3x, xy equals 1, and xy equals 3. So those last 2 are not lines, they're obviously hyperbolas. Okay, so let's sketch what this region looks like first. So notice if we have y equals x, that's going to be happening like exactly at a 45-degree angle. So there's our y equals x. Okay, great. And then next, our y equals 3x, so that's going to be another line which has a bigger slope. So I'm not going to worry about putting things here to scale because I just want to kind of get in my mind what this thing looks like. So there's y equals 3x. Notice xy equals 1 is the same thing as y equals 1 over x. So that's going to look like this. Good. So this is xy equals 1. And then xy equals 3 is the same thing as y equals 3 over x. So that's going to look something like this. So both of those are limiting to 0 right there, although I haven't really drawn that appropriately. Okay, great. So this is the picture that we've got. So what that means is that our region D is in here. Okay, good. So now we want to think about what would be an appropriate change of variables. And so I think it would be a pretty good choice to make one of our variables equal to x times y. So let's go ahead and set u equal to x times y. And then you might say, well, what should we let v equal? Well, it turns out that we can just let v equal y, and that will make it a little bit simpler. So let's let v equal y. Okay, good. Now let's solve that change of variables for x and y. So what this is going to do is that's going to let x equal to u over y, which is the same thing as u over v. So that means we have our change of variables. We have x equals u over v, and then we have y equals v. So there's our change of variables. So in other words, our transformation of the plane, TUV, is given by the vector UV, v. Okay, good. So now that we've got this change of variables, what I want to do, I'll bring that up a little bit, and then I'm going to draw my new region right there. So picking up where we left off, we drew our region, we made our transformation, which was given by u over v comma v. In other words, x equals u over v and y equals v. But now what that tells us is that this curve right here will be changed into a curve in the uv plane, which is given by u equals 1. And then this curve right here will be changed into a curve which is u equals 3. And so if we make u the horizontal axis, those are obviously going to be vertical lines, which is nice. Now let's see what happens to y equals x when we transport them into the uv plane. So notice that if we have y equals x, okay, so let's do this substitution. So that's the same thing as saying v equals u over v, which means that we have u equals v squared. So u equals v squared, or v equals the square root of u. That's going to be a parabola on its side. Okay, good. And then similarly, if we have y equals 3x, that's going to give us v equals 3u over v. In other words, u equals 1/3 v squared. Okay, so let's go ahead and point those out over here. So this is going to be the same thing as u equals v squared when we transport it over into the uv plane. And this is going to be the same thing as u equals 1/3 v squared when we transport it over to the uv plane. So now that we've figured that out, I'll erase this bit and then we'll draw the picture of what we get. So now that we've sorted all of this out, we're ready to draw our picture of what's happening in the UV plane. So let's see, here we have the U axis and the V axis. So notice that these two blue lines are going to turn into vertical lines, u equals 1 and u equals 3. So I can draw those like this. Great. So that is 1 and 3. Good. And then these two red lines are going to turn into the parabolas u equals v squared and u equals 1/3 v squared. And those look like the following. Okay, so this one at the bottom will be given by u equals v squared, and this one at the top will be given by u equals 1/3 v squared. Now it's also going to be useful to write those in the other format. So this is going to be the same thing as v equals the square root of u. Since this is all happening for positive u, that's like good enough. And then over here, this is going to be the same thing as v equals the square root of 3u. Okay, good. Now it's kind of clear why the one that's on top is on top. Okay, so now this is our region, maybe we could call it d bar, which is happening over here in the UV plane. Okay, so now we're done with this picture. Notice we have a much simpler picture here. It's a type 1 integral. So we can go ahead and erase this and then calculate the integral in the UV plane using methods of type 1 integrals. So now we're ready to go. So we know that this is going to be equal to the integral over d bar using our change of variables, where d bar is that thing that's happening in the UV plane. Now let's replace x, y with what we need to replace them with. So that's going to be u over v for x times v for y. So that's kind of nice. And then we have the absolute value of the Jacobian, so partial xy by partial uv. And then we have dA bar, where that's understood to be happening in the UV plane. Okay, good. So now this is going to be the double integral over d bar of, well, so u over v times v is the same thing as u. And now we have the absolute value of the determinant of our 2x2 matrix made up of these partials. So the partial of x with respect to u, that's clearly 1 over v. The partial of x with respect to v is going to be minus u over v squared. And then the partial of y with respect to u is 0. The partial of y with respect to v is 1. So we get something like that. And then we have dA bar. Okay, good. So let's see. I want to leave that picture up. So what I'll do is, well, I'll fit it in down here. This is going to be the integral over our region d bar of u. And then let's see what we get for this determinant. We're going to get just 1 over v. 1 over v, and notice the absolute values don't do anything because all of this is happening in the first quadrant over there, dA bar. So now I'll bring this up and then we're pretty close to finishing it off. Okay, so to finish it off, we have our goal double integral is the double integral over d bar of u over v dA bar, where this is happening in the UV plane. So notice this is a type 1 region in the UV plane. So that means I can write this as the integral from 1 to 3 of, that's happening over, the outer integral will be du, the inner integral will be dv, and then I have u over v. Okay, and so let's see what's happening with the v bounds of integration. So notice the smallest value that v can take on is the square root of u, and the largest value is the square root of 3u. Now we have a nice iterated integral, which means we have just a couple of calculus 1 problems to do. Okay, so from here, this is going to be the integral from 1 to 3 of, so notice that u is a constant, so the inner integral will be u times the natural log of v. We're going to evaluate that from root u to root 3u, and then du. Okay, good. So notice that's going to be the integral from 1 to 3 of u times the natural log of the square root of 3u minus the natural log of the square root of u. So we've got something like that going on, and then du. Okay, so now we're done with our picture. I'll clean up that picture and then we'll just continue this on the other side. Okay, the next thing I can do is I can use logarithm rules here to combine those two guys. So that's going to be equal to the integral from 1 to 3 of u times the natural log of this quotient, square root of 3u over the square root of u. But notice that's going to simplify down to the log of the square root of 3. So that's going to give me the integral from 1 to 3 of u times natural log of root 3 du. Okay, so notice I can bring my natural log of root 3 out like that, and then I have the integral from 1 to 3 of u du, but now I'm almost home free. Notice the natural log of root 3, we can use a simplification formula on that. So root 3 is the same thing as 3 to the half. So this is 1/2 natural log of 3. Good. And now I can take the antiderivative here. This is going to be u squared over 2 evaluated from 1 to 3. So let's see what we get. So this half will combine with that. We'll get 1/4 times the natural log of 3 times the quantity. So we've got 3 squared minus 1 squared. That is 9 minus 1, which is 8. Good. So in the end, we will get 2 times the natural log of 3 for our solution. 8 times 4 is obviously 2. Okay, good. So this is a good place to end this video.